Analytic approximation for the Dirichlet problem. Why are we doing this? Although Maple can solve some elliptic boundary value problems analytically, it does not have a numeric solver for such problems. In fact, as recently as August 22nd of this year, 2023, there's a Maple Primes post Laplace equation that asked how Laplace's equation could be solved numerically in Maple. The discussion went on a bit, and I added a pointer to the recorded webinar, Maple-based numeric symbolic techniques for PDE boundary value problems. And that technique was essentially finite difference. The discussion continued. Finite differences are difficult to implement on arbitrary domains. So finite elements are essential, and that's really what the industry standard is. And Dr. Venkat Subramanian, who does a lot of work in this area, Maple user, posted pointers to work he has been doing in conjunction with Maplesoft to resolve some of these computational issues in Maple. Apparently, Maple is building some of the tools, and people like Venkat are putting these tools to work together to solve these kinds of boundary value problems. So this present webinar explores an analytic approximation scheme that Kantorovich and Krylov first published in their mid-1930s text, Approximate Methods of Higher Analysis. So today's presentation is based on something from the 1964 Benster translation of that pre-war text. The Maple Primes post Laplace equation, I think, highlights the appeal of an analytic approximation scheme given Maple's weakness in this area. So what's the theory behind this approximation technique? It applies to elliptic equations, not only Laplace's equation being elliptic. That's the example that was in this text that Kantorovich and Krylov used to illustrate the method. Okay, so use the unknown. M is the elliptic operator. It satisfies boundary data on a contour that defines the region. And P can be some homogeneous linear operator on that boundary. So here are the steps to the method. You get an infinite set of harmonic functions for Laplace's equation, or an infinite set of solutions to the partial differential equation. Don't worry about the boundary conditions. Parameterize the boundary using arc length as the parameter. Evaluate these functions U on the boundary. They become functions of the arc length parameter. Call them phi k. Orthonormalize them. Call them psi k. Expand this boundary value function as a series in these psi k's. Call those coefficients ak. Use those coefficients ak in a linear combination of these functions uk. That sum is the approximation to the solution of the boundary value problem. So for our operator, which is the Laplace operator, these functions are harmonic inside the region. These phi k's are these harmonic functions evaluated on the boundary. They are then orthonormalized. They form the psi k. you do this Fourier series type expansion to get the coefficients AK, and you make this linear combination. That's the approximation. Now, Kantorovich and Krylov in the mid-1930s are using a pencil and paper. They end up giving a two-term solution to example 1, which I'm going to reproduce here. And we'll do it in Maple to illustrate that process and to demonstrate the power of Maple's computational tools. So what is this first example that we're going to do that we took from Kantorovich and Krylov? Well, what is the boundary value problem we want to solve? Laplace's equation on a square from -1 to 1 in each direction. Boundary data, 1 minus y squared on left and right, 1 minus x squared on top and bottom. Now, Maple can provide an exact solution to this boundary value problem, and we'll find it so that we have something to compare to. Now, in order to apply all 4 boundary conditions at the same time, it turns out you need to translate the square so its lower left corner is at the origin. So here are the equations by which we make the shift. These are now the new edge conditions. Instead of the unknown being u, it's now w as a function of alpha and beta. Here is the Laplacian on w. We applied a ptsolve command to this equation with these 4 boundary conditions. This is the solution Maple returns, an infinite sum. It's an analytic solution. We simply shift back so that we are looking at x and y, and then we change this infinity to a finite sum. I picked 10. So this is a 10-term partial sum. This is a graph of this U10. And this is what the edge looks like. I have graphed an edge from U10, and I have graphed the actual curve, the boundary data, 1 minus x squared, and you can see the red and the green lie on top of each other. It appears to be an excellent fit. Now, Kantorovich and Krylov in their book claim that at the origin, that would be right here, the solution should be 0.816. Now, if I evaluate U10 at the origin, I get 0.821. So there is now the question of how exact was the computation that Kantorovich and Krylov were able to do using a pencil and paper. To be sure that this U10 is carries enough terms, I went out to 20 terms, evaluated at the origin, and I get to the same exact number. So U10 is fine for our checking and our approximation. So now let's obtain the Kantorovich and Krylov approximate solution. Remember, there are some steps that we have to go through. First one is to obtain, in our case, harmonic functions because we're using Laplace's equation. And you can see here that I'm making use of some of the Maple tools. I'm going to work with the student vector calculus package. I want solutions to Laplace's equation, and Maple says 2 arbitrary functions, one with argument y minus ix and one with argument y plus ix. So I thought about that for a minute. I says, I will take just polynomials, and I will take y plus ix to the n, and I'll take the real and imaginary parts, and that will give me a bunch of harmonic functions. I begin by applying eval c to the real part. I generate one solution is a 0, and I remove it. I don't want the 0. So I get this sequence, put them all in one big set, and you can see this is the 0 order term, is one of them. This is first degree pair. This is a second degree pair. Pair. This is third degree, and so forth, out to an 8th degree polynomial. The next step is to apply the Gram-Schmidt orthonormalization process to these harmonic functions. So in order to do that, I'm going to define the polygonal path around our square, starting at 1, 1. You notice I end up over here at 1, 1 to complete the loop. So, Gram-Schmidt process. This is the first one, and I'm using Maple's path int command, which is the line integral of a scalar. This is the scalar. Then I normalize that first function, and I get psi 1. Here I'm simply counting how many of these polynomials I have in here. I think it's 17. So you subtract off those components along the previously computed psi's. And then I normalize that particular function. Again, using path int, you divide and you get psi k's. What do these things look like? Well, this is the constant term. This is the pair of first degree terms, and so forth. Now, just take a look at that. Imagine doing that with a pencil and paper. Just think about doing that with a pencil and paper. So the next step is to expand the boundary data in terms of these functions psi k. Well, we now need to break the contour into its 4 separate pieces. So I define these pieces that the path in command will understand. A line between these 2 points, these 2 points, these 2 points, these 2 points. Those are the 4 edges of the square. So we need to do a path integral of the function, boundary function, with the psi k along that edge, that edge, that edge, that edge, and there are 4 edges, so you have this sum. This gives me a list of numbers. Call that list A. And you'll see there's a lot of zeros in here. There's 3 non-zero terms and a bunch of zeros. Now, Kantorovich and Krylov got rid of these zeros by a symmetry argument that I didn't have to worry about, because I was just waiting to see what Maple would do. I threw it at Maple. Maple says, fine, I'll give you the zeros where the zeros belong. So I had these 3 non-zero coefficients. And I will form 2 approximating sums. 2 terms using these 2 coefficients, and 3 terms using all 3 of these coefficients. And you just form the appropriate linear combination. This is what those 2 approximations look like. This is the 2-term approximation, and this is a 3-term approximation. And now we want to test the accuracy of these approximations. 507 is an approximation to pi. It's not a very good approximation. So unless you have a way of testing how good the approximation is, anything is an approximation to anything. So let's test the accuracy in as many ways as we possibly can. So first of all, I have graphed this approximation on its edge and compared it to what it should be. So what it should be is in black, and what it is approximately is in red, and it's close, but it doesn't win a prize. The three-term approximation, the red and the black are indistinguishable. This is the solution surface. U10 is in green, and the two-term approximation is in red, and they're intermingled. They're close, they're intermingled. And this U10 and the three-term approximation, again, close and intermingled. Let's get some numbers. This is a graph of the absolute value of the difference between U10, which is our exact solution, and the two-term approximation. And these spikes in the corners are on the order of 0.05. For the three-term approximation, it's on the order of 0.01. So you have a sense of how big the differences are. Here, I'm asking Maple to give me the maximum value of the difference between the exact and the approximate, and the maximum value of the absolute value of the difference between the exact and the approximate on the square. And you see here the maximum is on the order of 0.046, which matches what you see in the picture. And here you see it's on the order of 0.011, which is on the order of what you see in this graph. Now, as a final note here, this is the solution, the two-term approximation that Kantorovich and Krylov ended up with. This is how they wrote it. This is exactly how they wrote it. And you can see they had it working with floats in some places, and the exact numbers like a sixth in other places, 2/3 over here. This is what they ended up with. This is what we would have gotten if we worked with a pencil and paper. You saw what we got when we worked with Maple. The equivalent of this in the yellow box is what we got in Maple. Now, how big is the difference between the Kantorovich and Krylov version of this approximation that we got in Maple? The difference is on the order of maybe, 8/1000ths, and the biggest difference occurs somewhere near the origin. Now, Kantorovich and Krylov used their solution here to evaluate it at the origin and make some statements about accuracy. I think these figures and these computations do a better job assessing the validity of the approximations. Well, I was pretty satisfied with the outcome of that first computation, that I could reproduce what Kantorovich and Krylov had articulated in their text. I said, but I want to do this on some other regions, some other boundary value problems, and see if this method is robust. So I picked these three problems: ellipse, triangle, and a region bounded by two arcs. So let's see this ellipse problem. What is the boundary value problem I'm going to tackle? First of all, I needed an ellipse. So here's an ellipse. It's this way. It's a long, skinny one like that. And I started with the answer because I wanted an exact solution I can compare to, and finding the exact solution on an ellipse is a real challenge. So I worked backwards. So I picked this harmonic function. I'll show you in a minute how I got it. And then I evaluated it on the ellipse to get the boundary data. This is what the solution surface looks like as it sits over the ellipse. And this is the edge data. This is this function. Now, how did I get this? V is the imaginary part of this linear fractional transformation, and the boundary function is just V evaluated on the ellipse. So I will have an exact solution to compare to when I do this approximation. Okay, to get started, I reinitialized and began Maple clean. So I did a restart, brought back the vector calculus package, and here is how I created that function V. So here's G, and I used the context panel over here. Let's see if we can get the context panel to show you what I did. It doesn't want to show you. Assign function, and it does the work of defining this function. So I take the imaginary part of G of x plus Iy, and you got to hit it with an eval C because there's these parameters. It'll simplify. That's where I get this function V. It's harmonic. Now I got to generate these polynomials, UK. Do it the same way I did before. I take polynomials, evaluated y plus ix. There's one that comes out to be 0. I knock it out. Put them all back together. I have this string of polynomials. My path is an ellipse, and I can define ellipse, and the path in command will understand that. And if you'll notice right over here, I have got a decimal point, and that will kick the integrations into numeric mode. Otherwise, I'm going to get elliptic integrals, and then I'm going to get expressions swell of unimaginable size. So I've got to do numeric integrations here. The next step is the Gram-Schmidt orthonormalization process, and I do it just like I did before. I'm using the path in command, integrating a scalar around this ellipse, and here's where I normalize. Here I'm counting up the number of polynomials up in this list, and then you subtract off the components of along the previous size, and then normalize. So this is the normalization step. The F normal, there's a bunch of very, very small terms that the F normal knocks off to 0. Here's what they look like. Remember, I had to do it in floats, otherwise I was going to get elliptic integrals. And look at that and ask yourself, could you do that by hand? Could you do that with a pencil and paper? I don't think so. And that illustrates the power, the utility of a tool like Maple, is to expand. The next step is to expand the boundary function in terms of these psi k's. So here is the integration step, path in. Simply give it V and let the path in command figure out that it has to evaluate V on this ellipse. The F normal and the simplify clean things up. This is the list of coefficients that you generate. A couple of zeros, another 0 in here, 0 over here. The approximation is the linear combination of these coefficients and the psi k's, And this is what that approximation looks like. So again, we have an approximation. It's meaningless unless we can, in some way, test the accuracy of that approximation. So we first drew some graphs. As we did before, we have here the exact solution, which is little v, and the approximation, which is big V, little v in green, big V in red, and you can see they're pretty much mashed together. Here we look at graph of the absolute value of the difference between the exact and the approximate, and the biggest peak seems to be 5, 6, maybe 7 1,000ths. Here I'm looking on the edge, so this is the absolute value of the difference around the boundary. Again, you can see here the peak seems to be around pi and 7 1,000ths. Here I've superimposed the exact and the approximate along the boundary, and the two curves seem to lie one on top of the other. Here I'm looking at the inf norm, or in other words, the maximum value of the absolute value of the difference between the exact and the approximate, and it's 7 1,000ths, tiny bit more. A third problem is a Dirichlet problem on a triangle. So let's see what the boundary value problem actually is. I'm using the same harmonic function, and here's my triangle. Nodes are, or vertices are 0, 0, 5, 4, and 0, 7. This is therefore the y-axis. Here are the edge equations. Here are the values of this harmonic function on those edges. This is the solution surface as it sits over the triangle. What I've done here is I've graphed these arcs separately on each edge of the triangle, because later I'm going to compare these exact arcs to the approximate arcs that I generate. And again, I'm going to use this function g to generate the appropriate psi functions. So in order to solve this problem, I'm going to initialize again, as we did before. So there's a restart, bring back the student vector calculus package. Here's the function g. I use g to generate the bits that I need. So that gives me v. G of x plus iy. Take the imaginary part, hit it with an invalid c because there's a parameters x and y. So that gives me v, and from v I get the other bits I need. Again, I generate polynomials. I use y plus ix to the n. Real part, because I have parameters, I hit it with an eval c. This generates a zero term, and I want to remove that. So here are the list of polynomials that I'm going to use as the phi functions. And now I need the line segments option for the path-in command. Going around the triangle, you start at the origin, and you got to make sure you come back to the origin, so you close the loop. The process is exactly the same as we've done before, and it's the fact that we can just implement these same steps in different circumstances that illustrates how powerful it is to have a tool like Maple. So the next step is to orthonormalize these phi functions, use Gram-Schmidt process, just as we did before. We use the path in command around the triangle. This defines going around the triangle. You can see the normalization here. So we get psi 1. Here I'm counting up the number of polynomials in that list. Subtract off the components along the previous psi functions, and then normalize. So here I am doing the normalization step. You get the length, and then you divide by the length. Here's some simplifications. F normal knocks out stuff that should be 0. We'll simplify, get the psi k's. This is what they look like. I don't think you would want to do that with a pencil and paper. So just as before, we expand the boundary function in terms of the psi k's. So you have integrals to perform. So v times psi k, and the path in command is smart enough to say to v, I will evaluate you just on the boundary. You don't have to worry about that yourself. Again, an F normal to knock out stuff that should be 0. Simplify and float this stuff. Otherwise, you're going to get terrible expressions swell. Here are the coefficients. The approximation is a linear combination of these coefficients with the psi k's. This is what that approximation looks like. And as we've done before, we want to test the accuracy of this approximation. I mean, we can write anything down at all and say it's an approximation to whatever we want, but if it's not a good approximation, it's valueless. So you've got to test the validity of the approximation. And so here I have graphed the exact solution, which is what we started with, and the approximate solution. And you can see the red and the green are intermingled. They're pretty tight on. Numerically, let's see what we can do. So this is a graph of the absolute value of the difference between exact and approximate. It would appear that maybe 7 1,000ths might be the height of that peak. And here we're looking on the edges. So on each of the 3 edges, we have the exact curve in green and the approximate edge value in red, and they are very close graphically. Here we are graphing the absolute value of the difference between exact and approximate on each of the 3 edges, and you can see here approximately 7 1,000ths. Here it's smaller, maybe 3 1,000ths and 7 1,000ths. We can do an inf norm and compute the maximum of that difference between each on each edge, exact and approximate, and because here I'm looking on the edges, and you can see what the numbers are. Roughly 7 1,000ths on these 2 edges, and no more than, well, 3 1,000ths, so it's like 28 over here, so no worse than 3 1,000ths. So the approximation is easy to get, pretty accurate, and it's an amazing piece of work for something that was first published in the mid-30s. And at that time, these approximations would be really hard to get by hand But doing it in Maple, it's not hard at all. And finally, for a fourth problem here, Dirichlet problem on a region bounded by two arcs. And these two arcs are curves that I've used in the creation of many examples that I've put together for students over the years. All right, so we do the same strategy. This is the same harmonic function. Here are the two arcs, piece of the sine curve, piece of the cosine curve. Put them together. This is the region. You can see the two arcs. This is what the solution looks like on that domain bounded by those two arcs. And then these are the function values along those two arcs. Same strategy here. V is the imaginary part of this function g, linear fractional transformation. I've got something I can compare against. In order to generate the approximation, we'll begin from the beginning, initialize again, restart, bring in the student vector calculus package, define the function g, take the imaginary part of g of x plus iy. You need an eval c on here because the parameters x and y. Hit it with a simplify. That's how we get v. Use polynomials, so we take y plus ix to the n as our polynomials. Those will be the uk, the real and imaginary parts of those polynomials. That gives us the UKs. From the UKs, we get the phi's. So here are the phi's. I've knocked out a zero term. Here is the list of polynomials that are the phi k's. There are two pieces to the path, and we define them separately, the sine piece and the cosine piece. And here's a quirk that I ran across. You would think that you would go, and let's look at the picture again. You would go pi upon 4, to 5 pi upon 4, and then 5 pi upon 4 back to pi upon 4. Well, when I tried that, things didn't work properly. Each arc had to be defined from pi upon 4 to 5 pi upon 4, and that surprised me. So the next step is the Gram-Schmidt orthonormalization step, and here we had to be a little bit careful because there are two pieces of the arc of the boundary, two different arcs, two different functions, and you have to do a path int on one of them and a path int on the other one, and you have a plus sign. Well, I didn't want to have to keep writing these two different path int commands, one on the cosine and one on the sine. So I wrote a little procedure. Integrate on C. Integrate on the complete contour. And that procedure does the addition over the two pieces for me so that when I define these psi functions, I can use integrate on the complete contour instead of having to write these two separate path int commands. But the process is the same. Get the length, divide by the length, and you get psi 1. Count up the number of items in the list of phi functions. Subtract off pieces of the next phi function that's along the previous phi functions. Then get the length, divide by the length so you normalize, float everything so that you don't have expression swell. The simplify and F normal knocks out stuff that should be 0. Got the psi k's. You want to see what they look like? Here's what the psi k's look like. Formidable, simple in Maple. Would not want to have to do any of that by hand. So in a pencil and paper world, this is not a useful technique. You're not going to get high accuracy. You can't add more terms because the work is enormous. In Maple, it's feasible. The next step is to expand the boundary function in terms of the psi k's. That gives us these coefficients A. So again, I use this integrate on the complete contour. You put V, the integrate, the path in command hiding in here is smart enough to evaluate V on the boundary. An F normal and a simplify knocks out stuff that's almost zero and renders these things as floats. So here are the coefficients. From the coefficients, you make this linear combination. Those are the coefficients with the psi k's. That gives us this approximation. V, this is what the approximation looks like. Again, we have something we're calling an approximation to what we want. Anything is an approximation to anything. It just depends on how good the approximation is. So we've got to have a way to test the accuracy of the approximation. And here I have graphed the exact solution and the approximate solution, exact in green, approximate in red, and the red is so embedded in the green you can't tell it apart. Here I've attempted to get some numeric data out of a graph. So this is the graph of the absolute value of the difference. It seems to spike here a little over 3 100,000ths. Exceedingly accurate. Amazingly accurate. Here I'm looking at the edge, the sine and the cosine curves that make the boundary. Exact in green, approximate in red, same thing here. One curve lies on top of the other. Here I'm looking at the difference on the bounding edge. Here it's cosine, here it's the sine. 3 100,000ths, 3 100,000ths at worst. And here, using the inf norm, finding out where is it the worst. So the maximum of the absolute value of the difference on the cosine part, on the sine part, and you see it's 3 100,000ths. Amazingly simple in Maple. Amazing piece of approximation. And what I have done is not what you see in a typical textbook. In a typical textbook, you see a statement and immediately authors rush into the proof, and they think that by proving they have explained. And I find that you cannot explain until you've seen examples and done some computations and seen what's involved. And then the proof, when it comes, is much more understandable. And I have not bothered with the proof here. The proof is in the book. Get a copy of the book and find the proof if you're really interested.